So in this class, we are going to talk about Fresnel diffractions. So we are going to talk about how the Fresnel diffraction can be actually calculated, the calculations. And two examples will be discussed. The first one is the Fresnel diffraction by square aperture. Remember that in the case of a Fraunhofer, we have this aperture. And you can see at the plane we get sinc function and sinc function like this. Okay, so that was the Fraunhofer. And we'd like to know how this, in this case we have a square, that means that this side along the horizontal axis and this side on the vertical axis are the same. And then we are going to look at how Fresnel deflection is going to change as a function of a z. So first thing we need to know is that Fresnel diffraction is actually z dependent. In contrast, Fraunhofer diffraction did not depend on the z. So because it is just simply a Fourier transform, but actually in the case of the coordinate x over lambda z, y over lambda z, so actually it is given as a function of x over lambda z and y over lambda z. So it is dependent on the z, but actual pattern itself is not dependent on the z. Okay. So we are going to look at how the z-dependent Fresnel diffraction will evolve for the case of a square aperture, and then second thing is that Talbot imaging, which is a kind of a phase grading, and that we'll see it's a kind of amplitude grading, and that we'll see how it goes. That means Talbot imaging is that it does not it repeats itself without any imaging optics, without any lens or any other complicated imaging system. In the special case, by simple Fresnel diffractions, you can get the exact replica, exact copy of aperture plane image. So let's start with the square aperture. So we have a width of 2w, that means, and then along the c-axis, along the eta axis, they have all w widths. Minus w, w, and have a plus w, minus w. This is our aperture, and then we have two forms of Fresnel diffractions. One is the convolution form, and the other one is the Fourier transform form. And then let's try to use the convolution form. And then in the case, because of a rectangular function, the integral over the infinite space now becomes a minus over a minus w2 w for the c, and then of course, and for the minus w2 to w for the eta. Okay, and then within inside we have a 1, outside is 0, and then we have this quadratic phase. Remember that Fresnel diffraction has this quadratic phase, and then this is what we get. This is 1. Okay, and then if you look at it, it is function of a eta alone and function of a C alone and the function of eta alone, so that you get this uxy is given by this one, ix and iy. So if you look at it, this is the C alone, and then you get the function of ix times iy, ixy is a variable, can be separable like this. Here, the ix is given by these functions, and the iy is given by this function, and we need to calculate this integral, and then everything is solved. Ix times iy, and we are going to change the variables from c minus x is going to be alpha, eta minus y is going to be beta, and then it becomes like this. Okay, and you get the identical integral form, and we are going to define the Fresnel number, which is given by this one. So if z is very large, then nf becomes very small. Okay, so depending upon z, you get the different nf. So if nf is very small, that means you have a very long distance from the aperture plane. And then in terms of nf, this alpha 1 and alpha 2, beta 1 and beta 2 is given by this one. Okay. And then if we change the variables, exponential ix is given by cosine x plus I sine x. And we are utilizing these equations. Then ix, this integral ix is given by this one. And then this is the so-called Fresnel cosine and the Fresnel sine. And here is the intensity wave field is given by C S here, so that Fresnel integral, Fresnel cosine, and Fresnel sine functions are given by. Okay, so if you want to find out what they are, you need to go back to section 2.2 and 4.2. But basically, instead of this function, you get the cosine j pi over 2 alpha square, okay, plus I sine j, I'm sorry, this is pi over 2 alpha square, like this. So it is basically cosine x square dx, okay, is the Fresnel cosine, and this is the Fresnel sine. So if you know the Fresnel cosine and the Fresnel sine, then you get the ix and iy, and then you get the intensity pattern is given by this this manner. Okay. So if you go by the alpha 1, alpha 2, beta 1, beta 2, so alpha 1, alpha 2, all of them are actually depending upon nf and capital X and capital Y, which all depend on z. So alpha 1 is a function of z, alpha 2 is a function of z, beta 1 is a function of z, as well as beta 2 is a function of z. So everything is function of z. So that is important. So as a function of nf or a function of z, so note that nf is given by w square over lambda z So we have a 0.01, 1, 4, 10. So 0.01 is a small number, so that means z is far away from the screen. And then as NF increases, it's getting to the closer to the aperture. So it's a function of z as well. So it starts from this kind of a wiggly pattern, and then eventually goes to sinc function. Sinc function. Okay. So this part is the Fraunhofer, and this part is Fresnel. Okay. So note that Fresnel cosine sine is actually given in MATLAB. So you just call those Fresnel cosine and sine, and then you can just calculate them. And now we are going to, excuse me, Fresnel diffraction by sinusoidal amplitude grating. Remember that in the case of amplitude grating for the Fraunhofer, we get zeroth order, and first +1 -1. We get this one, and then we'd like to know what's going to happen between the Fresnel. Once again, we are going to use this one over the rectangle. So in this case, it's a little bit different. It's not the what should I say? It's not the rectangle. It's not over the rectangle. It is actually face. It is extending infinitely, so that we have a. So along the C, you get this kind of a amplitude grating, and over the eta, it doesn't change at all. Remember that it's a function of a C, so it does not depend on eta. And then we have this kind of a period, capital L. So it is kind of a amplitude grating. So amplitude is changing, but we have a very infinite plane. And now we are going to assume that this has been illuminated by the plane wave. Okay. So this is what we get. So along the horizontal axis is modulated by this way. And then we'd like to know how it looks like. Okay. And we'd like to utilize the transfer function approach, equation 4.21. And then the solution begins by the first finding the spatial frequency spectrum. The field transmitter structure is given by this one. Remember that this is actually can be decomposed into two exponential function. And then we have Fourier transformation of transmittance is given by this one. Okay, then what we get is that we know that the actual pattern is the convolution of this one, and then impulse response function. Okay. Convolution of these two, but in the Fourier domain, it's just a multiplication of these two. Okay, you just multiply them together, and then you do the inverse Fourier transformation. So Fresnel was actually convolution of our U with H. Okay, but in Fourier domain, if you do the Fourier domain, is the Fu multiplied by Fh is nothing but transfer function. And then we have found out that transfer function for Fresnel diffraction is given by this way. And then we note that Fu is given by this one. So in the Fourier domain, we just multiply them together and then do the inverse Fourier transformation, and we get the convolution, which is Fresnel diffraction integral. And then we get the above function has a value unity at the origin, and when evaluated frequency, use this one. And then we have this kind of approximation, but anyhow, what we end up with is this that inverse transforming of this spectrum, which is Fourier transformation of TA times H, and then our field is given by so TA convolution of H, our Fresnel integral is given by this one, but in the Fourier domain is multiplication of each of them, and then we know what they are, and then we do the inverse transformation, and we get the Fresnel integral, and this is what we get. And furthermore, we get this kind of patterns, and then intensity is given by this one. And if you look at it, this is what we get. So do we have initially we have a plane, is aperture plane. And then we have a plane wave incident. And then we have this kind of images, and then we get periodic appearance of exact replica of our grating. So it has the same structures, and we call it Talbot image. So that by diffraction, Fresnel diffraction, and we get the replica of images periodically with this period. So this is another interesting phenomena of Fresnel diffractions. So this is the end of this class. So what we have done is that we have seen the square aperture, and we have seen how it evolves like this, starting from the Fresnel diffraction to the Fraunhofer diffractions, which is the sinc square. And we have seen another case, which is the amplitude grating. And then within this, we could get the same image as diffraction grating, Talbot. with a period of a certain period is repeat itself. Like this, okay? And then we have a type of sub-images, and then if you look at it, the amplitude grating period is changed, okay? So you will see that twice the frequency of original grating sub-images. Okay. So this is the end for the Fresnel. What we know is that Fresnel diffraction can be generated either from the Fresnel cosine, sine, or we can have if we do know the transfer function, and then we can utilize the convolution. Okay. So either way, we can do it. Okay. So we will try to talk about how to actually calculate this Fresnel and the Fraunhofer diffraction with the MATLAB in the next class.